All right, so in this section, we're going to take a look at some of the chemical properties, which simply means the chemical reactions that the monosaccharides are going to undergo. And the first set of reactions that we're going to take a look at are oxidation reactions of the monosaccharides. Right, so remember when we talked about oxidation before, we said that oxidation could mean a couple things. It could mean adding more oxygens. It could mean increasing the number of bonds to oxygen, or it could also mean removing hydrogens, right? So any of those three, a combination of all of them or one of them, will tell us that oxidation is going to be occurring. So the key thing about our monosaccharides that we want to focus on when it comes to oxidation is that in solution, right, we said the monosaccharides typically are going to be in the ring form, but keep in mind that they still also exist in the open chain form. All right, and that is extremely important because what that means is that in the open chain, they're going to have that exposed aldehyde, which is going to be this functional group here in the case of glucose, right? So the fact that we have that aldehyde exposed now means that we can oxidize it, right? And we saw this in the previous chapter. All right, an aldehyde can undergo oxidation to produce the corresponding carboxylic acid, right? And when we're looking at the changes to the molecule, that's the only part of the molecule that's going to change, which is where the aldehyde is located. So in the case of glucose, right, if this is our open chain form of D-glucose, this can undergo oxidation, and all we're doing is we're changing now this aldehyde group into a carboxylic acid group. Right? The remainder of the molecule doesn't change. So in other words, the aldehyde is the reactive portion or the reactive part of the molecule. So we can take advantage of this, the fact that we can oxidize an aldehyde, to see how these sugars are going to behave, specifically the monosaccharides. So the fact that that aldehyde can be oxidized means, and we talked about this before, if something is being oxidized, something else has to be reduced simultaneously. And the thing that is going to be undergoing reduction, right, we can make use of that in this particular process as a test for a sugar that can be oxidized. And if the sugar is being oxidized, something else has to be reduced, which means that that sugar is reducing something else. So we're going to call it a reducing sugar. Right, so a reducing sugar reduces something else as it becomes oxidized, right? Oxidation has to go hand in hand with reduction. So as the aldehyde here and the sugar is becoming oxidized, it reduces something else. And what it reduces in this case, we can take advantage of that. In this case, we're going to see a blue color associated with a solution. And we call that solution a Benedict solution. And that's due to the presence of the copper 2+ ion. And if we add a reducing sugar to that Benedict solution, that reducing sugar reduces the blue copper 2+ to a red, a brick red color. That's due to the presence now of the copper 1+ ion. All right, and what we'll see is that the solution actually changes color from that blue Benedict solution, which has the copper 2+ in it. It changes now to a brick red color. Right, so that's indicative. That's a very common test for the presence of reducing sugars. That's the Benedict's test for reducing sugars. Right, so it takes advantage of the blue color of the Benedict solution. And as that substance, in this case, it's a monosaccharide, if it can be oxidized, as it undergoes oxidation, it reduces the Benedict solution to that red color. And it's very, very, very distinctive. There's no mistaking if you have a reducing sugar present. So when that monosaccharide undergoes oxidation, right, it produces a carboxylic acid, and because it came from a sugar, we call it a sugar acid. Right, and like we said, it's produced in the oxidation of the aldehyde as the blue copper 2+ from the Benedict solution is reduced to the copper 1+. And we name the corresponding sugar acid by changing the OSE and replace it with an ONIC acid. So for instance, glucose undergoes oxidation and it changes to, now we drop the OSE and it becomes gluconic acid. Right, and the only change that's happening there is we're changing the aldehyde group to the carboxylic acid group. So because this sugar undergoes oxidation, that means it has to reduce something else. So that sugar then is going to be acting as a reducing sugar. So a reducing sugar then can be oxidized. In the case of fructose, which we know is a ketohexose, right? Fructose contains a ketone group in it, which typically, as we saw before in the previous chapter, ketones cannot be oxidized. But what happens when we have a fructose in that Benedict solution, that ketone gets rearranged and it actually forms an aldehyde, which can then become oxidized further, right? So fructose, even though it's a ketohexose, it still gives you a positive result for that Benedict's test. So there's fructose, our ketohexose. It undergoes rearrangement to produce glucose or to change into glucose, and then this then can be oxidized further to produce the corresponding sugar acid. So we see then that the presence of that aldehyde group in the sugar, the exposed aldehyde in an open chain form of the sugar, allows it to be oxidized. But the other thing that can happen to that exposed aldehyde or carbonyl, and again it's a reaction that we saw in the previous chapter, is that aldehyde can undergo reduction, right? Typically the conditions that we saw were hydrogen with some sort of a catalyst like platinum or nickel or palladium, and that aldehyde can then be reduced back into the corresponding alcohol. And we're going to see that happening here as well in our sugars, right? So if we have an aldehyde, for instance, in our sugar, and here we have D-glucose again as our example, Right, here's the reactive part of the molecule, the carbonyl, in the form of the aldehyde. That can be reduced back into our corresponding primary alcohol. So we just change the functional group to an OH. The remaining part of the molecule here doesn't change, right? So that's the same thing that we saw with the oxidation. The only part that changes was the carbonyl. And again here, the only part that changes is the carbonyl part of the molecule. And we have our conditions here, which are our, for reduction, the hydrogen and the platinum, right? Those are our reduction conditions. So we end up forming something known as a sugar alcohol. As our product. And sugar alcohols are sometimes referred to as aldehdols, and they're actually quite common things. So for instance, the way that we name then our sugar alcohol is we're going to drop the OSE ending and replace it with itol or itol, right? So glucose undergoes reduction to produce the sugar alcohol, which is glucatol. So we drop the ending, replace it with itol, and the common name for this is sorbitol. And that's a very, very, very common ingredient in lots of things, these sugar alcohols. You find them, for instance, in things like your chewing gum, right? So if you look at your packet of chewing gum, typically the first ingredient you'll see is some sort of a sugar alcohol. So in this case here, this looks like extra chewing gum. Sorbitol is the very first ingredient, right? And that's a sugar alcohol. But you'll see other ones as well. So xylitol comes from xylose, mannitol comes from mannose, etc. Right? So these are used commonly as sweeteners in several of the sugar-free products that you'll see. So those are sugar alcohols that form when your monosaccharides become reduced. Okay, so let's take a look at how we can put that into reaction. So it says here, write the product of the reduction of D-mannose. All right, so we have your sugar, and again, the reactive part of it is going to be where the carbonyl is located up here. Everything else is going to be the same. So we can draw the parts that don't change. So we're going to have a 1, 2, 3, 4, 5, 6 carbons. All right, so we can draw everything that doesn't change. And then the only thing that we need to change would be that aldehyde group. We're going to change it to the corresponding alcohol. So we're just going to change that double bond O to an OH and replace the remaining bonds to hydrogen. All right, that's the only part that actually changes. And then if we were to name this, the mannose turning into a sugar alcohol, we'll call this D-mannitol. Okay, and then the last section in this subsection talks a little bit about how we can take advantage of glucose being a reducing sugar, for instance, to test for glucose, and the fact that glucose can be oxidized means we can use it to actually determine how much of the glucose we have in the bloodstream, for example. So I'm not going to go through this. I think this is a really good example of an application of some of the reactions of our sugar, specifically the oxidation of glucose. So take a minute and just read through this. It actually talks a little bit about the test that's actually used to determine the level of glucose in the urine, for instance. All right, and that is all based upon the fact that your glucose acts as a reducing sugar, which means that it can be oxidized.